Today we're going to be looking at the subtle differences between the different pH curve graphs and understand why we have those differences, and then we're going to look at how we can get a pKa value from one of these graphs. And remember to download your own copy of this PDF so you can be making your own revision notes as we go through. So let's get started with a strong acid, strong base curve. So these curves are coming about from doing a titration experiment, and in all of our examples we are going to have the acid in the conical flask already and the base is in the burette. And what's missing from my diagram is a pH probe. So pH probe that is continually monitoring the pH of the experiment as the base is getting added. So the main point in all of these graphs is the pH at the start, the pH at the end, and the pH of the equivalence point. So the equivalence point is the vertical part of the graph. Just a quick reminder of our definition for equivalence point. So this is the point in which, in your titration, a stoichiometric ratio of reagents has reacted and the reaction is complete. All right, so back to our graph here. So with our strong graph, the pH is starting off low, and it's starting off low because it is a strong acid. And you can even calculate this pH if you wanted to, so don't forget, if you know the concentration of your acid, you can calculate the pH using our favorite equation that I've just written down there. And then, we have a very large pH range for our equivalence point. So this is a really good point. So this means here that not a huge change in volume, is causing a big change in the pH value. And then the final thing with our strong is the pH, or almost the final thing, is that the pH is nice and high, almost at 14, it could be around 14, again due to the strong base. And going back to the equivalence point, it is going to be around 7. So it's covering a large range, but it's definitely going to be around 7. Now on to a strong weak pH curve. So the strong weak pH curves, and again we're going to be looking at the same three things: pH at the start, the equivalence point, and the pH at the end. So we're going to start off with the strong acid weak base titration. So again, we've got a low pH at the beginning, and this is due to the fact that we are using a strong acid. So the strong acid in the conical flask. Then as we are adding the base, we're getting this region here. So this is called a buffer region, and this is because the pH isn't changing very much, even though we are adding quite a large amount of base. Again, we're going to go through this in a future video when we look at buffers, so watch this space. Then we have our equivalence point. So we've got a nice vertical part of the graph here. But we can notice with this equivalence point, it is below pH 7. So the finished product is below 7. And this is due to salt hydrolysis. So we're going to have a quick look at salt hydrolysis now, but the next video is going to go into this in more detail. So we could have, as our strong base, hydrochloric acid, and this could react with our weak base of ammonia, and this could give us our salt of ammonium chloride. And what is happening is that the ammonium ion is reacting with water and is forming a slightly acidic solution. So that is why the pH is below 7. We're going to go through this in more detail in a future video. Now onto the weak acid strong base titration curve. So the pH is much higher because it's a weak acid. So weak acids always have a pH that is higher than a strong acid. Then we have our equivalence point. So we've got a nice vertical point on our graph. So we've got our equivalence point, but we can see this time is above 7. And then again, this is due to salt hydrolysis. And in this case, it's making the solution slightly alkaline. But again, we're going to explain this in the next video. And then in this case, our buffer region is going to be over here. But what we do have is, because of the strong base, the pH is higher. Okay, now onto our final graph. So a weak acid, weak base. So it doesn't matter, yeah, well, they're both weak. So there we go, doesn't matter what you're adding to what. We can see here that this graph is looking very different to the others. And what it is missing is a lovely vertical equivalence point. So our equivalence point here is actually happening over a range of volumes, which is not ideal. And this is because, the main aim of a titration experiment is to find out the concentration of an acid or a base that you don't know the concentration for. And getting a nice clear endpoint, which should match up with the equivalence point, using the correct indicator, is going to give us, is going to make our titration experiment all the worthwhile. All right, so now onto our final thing. We can use a strong, weak titration curve to give us a pKa value. So we can use this graph here to calculate pKa, or pKb, depending if you're using a weak acid or a weak base. And it is really easy. So from the graph, we know what the equivalence point is, and we're going to add some numbers to this graph. So in our example here, the equivalence point is at 10 centimeters cubed. Then all you need to do is divide that number by 2 to give us the half equivalence point. So that's going to be 5. And then we use our graph to get the pKa value. So we just go up and then over, and then whatever this pH is, whatever the pH here is, that is exactly the same as the pKa value. And why is this the case? It's all down to maths. So let's have a look at how that works. So here is just a quick expression, which we can then write as a Ka expression. So at the half equivalence point, the concentration of the acid is the same as the concentration of the anion that has been formed. So what that means is we can cancel those values out because they are the same, which then leaves us with this expression here. So Ka equals the concentration of the hydrogen ion, and we can just negative log to the base 10 this, as P just means this. So pKa equals pH. There we go, nice and simple. Okay, so that's everything from me today. Thank you as always for watching, and remember to tell all of your chemistry buddies, the more buddies you tell, the more videos will get made. All right, catch you in the next one. Bye.